What if, one day, the sun hid something from us? What if, just for a few days, a traveler from another star slipped behind that blinding light, and when it reappeared, the sky was no longer quite the same? You see, in the final October of humanity's quiet calendar, astronomers noticed a guest, a fragment of another world passing behind the Sunday. They called it 3I Atlas, and from that moment, nothing behaved as it should have. It brightened too quickly. It burned a green so pure it made the sun look pale. And then, for a brief window of time, every telescope from NASA's to those in China went silent. No data, no light, just the hum of uncertainty. Well, you might think this is just another comet story, a block of ice and dust wandering through the solar system. But perhaps, it's something older. Perhaps it's a doorway. A glimpse back to a universe long before our own star was born. Because you see, 3I Atlas isn't just an object. It's a question. What really happened behind the sun? And how can so many impossible coincidences line up to create one event that should never have been? Before we go on, I'd like to ask you to subscribe to the channel and leave a like. My aim here is simple, to help you drift off to sleep while exploring the wonders of science. Where are you on the map? Let me know where you are in the world and what time it is in the comments. It's always fascinating to see who's joining us from all around the world. So, let's continue. When we speak of visitors from beyond the stars, we often imagine them as messengers of mystery, drifting silently through the dark. But 3I Atlas was different. It wasn't just a body of ice and dust, it was a fragment of time itself, older than our sun, older than the world beneath our feet. And that's the thing, you see, it's not supposed to exist. Not in the way it does. Astronomers traced its orbit and calculated its likely age, and the numbers whispered something astonishing, roughly 10 billion years. That's twice the age of our solar system, twice the time it took for Earth to form, for oceans to gather, for life to rise and look up in wonder. You might wonder, how could a fragment survive for so long, through so many cataclysms? Well, to answer that, we have to journey back, not through space, but through time, to a universe that was still finding its rhythm. Back then, the first generations of stars had already burned through their brief, furious lives. They were giants, immense and unstable, blazing for only a few million years before exploding into clouds of gas and dust. Those explosions seeded the cosmos with the first traces of heavy elements: iron, nickel, carbon, oxygen, the raw materials of planets, and, eventually, of us. But 10 billion years ago, the galaxy was still young, chaotic, filled with storms of radiation and gravitational tides. Stars were being born in violent nurseries. Whole systems were torn apart before they could even settle. So how, in that turbulence, did something like 3I Atlas form, and more importantly, how did it endure? Perhaps, it was forged deep within the core of a massive planet, orbiting a star that no longer exists. When that star died, its planets were flung outward, their remains scattered into interstellar night. And somehow, one of those fragments kept its integrity, wandering for eons across the void, until it found its way here, into the neighborhood of our Sunday. It's strange to think about, isn't it? That in the glittering coldness of space, this traveler may have been alone for billions of years. Every encounter with a star system, every near miss with a planet, would alter its path ever so slightly. Each deflection a whisper of fate. And after all those ages, it ended up here, gliding toward the sun in a curve so gentle, so precisely aligned with the plane of our solar system that many astronomers paused. Coincidence, perhaps. But coincidences, when they start to pile up, begin to look like patterns. When 3I Atlas was first spotted, most believed it to be a comet after all. That's what its light suggested. A faint, greenish halo, the sign of gas evaporating as it neared the Sunday. But something about that glow was off. It wasn't the soft teal of cyanogen or diatomic carbon that ordinary comets display. It was sharper, more vibrant, as if the object were reflecting not sunlight, but something internal, something deeper. It reminded some observers of aurora's light born not from reflection, but from excitation, from energy moving within. I suppose that's when the first real questions began. What could produce a color like that? What could survive for 10 billion years without being ground into dust by cosmic radiation? The solar system is a dangerous place. The galaxy, even more so. Every grain of interstellar dust, every atom of hydrogen it met along the way, would erode it bit by bit. Yet here it was, intact enough to be, seen, massive enough to form a tail, bright enough to rival the stars. You see, that's what makes 3I Atlas so remarkable. It's not just the age, or the orbit, or the color, it's the simple fact that it still exists. It tells us something about endurance on a cosmic scale, about how matter, under the right conditions, can hold its form against entropy for longer than we can easily imagine. And when you think about it, that's almost poetic. A relic from before the solar system, crossing our skies, reminding us that everything we are, every atom in our bodies, was once part of a similar ancient cycle. But then there's another layer to it. Because if it truly is a piece of a planet from a long-dead system, then we're not just looking at rock and ice. We're looking at history at geology from another sun, chemistry shaped under conditions no longer present in our galaxy. It's as if a message in a bottle had drifted through interstellar tides, carrying with it clues to worlds we'll never see. And so scientists began to compare it with other interstellar visitors. You might remember the first one, Oumuamua, discovered in 2017. A tumbling shard, cigar-shaped, dark, reflecting sunlight in a way that defied easy explanation. Some called it an alien probe, others a fragment of rock. Then came Borisov, a much more traditional comet, its gases and dust behaving just as models predicted. But 3I Atlas, well, it sat somewhere between them. Too stable to be mere ice, too strange to be simple rock. Astronomers used every instrument available: spectroscopy, photometry, orbital dynamics. Each measurement brought new puzzles. The spectra hinted at metallic elements, nickel, for instance, in unexpected abundance. That alone suggested that this was not a common comet. Nickel forms deep within planetary cores, under immense pressure. To see it so clearly meant that the outer layers, the icy shells, had long since eroded away. What remained was a remnant heart, the metallic memory of a world that had once circled a different sun. And that thought that this piece of matter had once been the heart of a world, well, it's almost too much to take in. Somewhere, long before Earth existed, there was another star, another system, where this fragment belonged. Perhaps it orbited a blue-white sun, burning far hotter than ours. Maybe it had moons, maybe oceans, maybe nothing but barren plains of metal and stone. Then, in some unimaginable catastrophe, an explosion, a collision, a collapse, it was thrown into the dark, exiled to drift forever, and now, by pure chance, it has crossed paths with us. But chance can be deceptive. When we map its trajectory, we find something eerie. Its path through the solar system aligns almost perfectly with the ecliptic, the plane along which all our planets orbit. That's an odd thing for an interstellar object to do. Most would approach at random angles, plunging in from above or below the solar system's flat disk. Yet 3I Atlas approached, almost as if it knew the way, as if it had rehearsed this journey countless times before. Of course, that's poetic thinking, not physics, but still, it lingers. How do we explain such precision in a universe so noisy, so chaotic? Perhaps it's a trick of perspective. Or perhaps, and this is where science begins to stretch, there's something about the galaxy's gravitational architecture that guides these relics along invisible highways, currents in space-time carved by the motions of stars and planets. If that's true, then 3I Atlas isn't an anomaly. It's a messenger from the deep structure of the Milky Way itself, a sign of the hidden order beneath apparent randomness. When astronomers modeled its potential origin, they traced its velocity backward through interstellar space. The vectors pointed toward a region between the constellations Lyra and Hercules, an area once home to dense star-forming clouds. Many of those stars have since dispersed or died. Could it have come from one of them? Could it be a survivor of a system extinguished before our sun was born? It's a haunting possibility that 3I Atlas carries within it the memory of a vanished sun, a light that no longer shines. And that, I think, is what gives this object its strange power over the imagination. Because it's not just about astronomy, it's about time. Time, not as we measure it in years or seconds, but as a vast ocean in which matter drifts. Each grain of dust, each rock, each fragment of metal is a traveler through that sea. Some dissolve quickly, others, like this one, endure for billions of years. Time is not a clock, it's a landscape we move through, and in that landscape, 3i Atlas is a mountain, a survivor from an older world, standing alone against the erosion of eternity. Still, there's something uneasy about it. Its behavior near the sun defied expectations. It brightened too rapidly, as if some internal engine had awakened. Its emissions suggested not just reflection, but activity jets of gas and dust, released in ways that didn't fit the usual patterns of sublimation. Perhaps it was spinning unusually fast, or perhaps its shape focused sunlight into bursts of heat that triggered uneven outgassing. But as the data piled up, the explanations became less satisfying. So scientists began to look closer, to measure its rotation, its composition, its orbit. They noticed that its tail, for a time, didn't behave as it should. It seemed to bend toward the sun, rather than away. Radiation pressure should push dust outward, yet something else appeared to guide it. A magnetic field, perhaps, or a peculiar geometry of jets. It was as if the object itself was resisting the ordinary rules of cometary physics. And as October wore on, as the object slipped behind the sun and out of sight, the story grew more curious. The data stream from several observatories fell silent. Images stopped, arriving. For a few tense days, no one knew what was happening. Then, when it re-emerged from behind that blinding light, it was brighter, bluer, and some said changed. What could have happened back there, in the shadow of the sun? Did it fragment? Did it release some trapped volatile gas? Or did we simply misread the light, fooled by solar interference? These are the questions that keep astronomers awake at night, staring at lines of data that refuse to fit. Because sometimes, the universe gives you an answer that doesn't belong in any of your equations. And so, the investigation deepened. What was this thing really? A comet? A metallic shard? A remnant of a planet that once circled a dead star? Or something else entirely? Something we haven't yet found the words for? The search for that answer would lead scientists to examine its orbit more closely, to notice just how unnervingly precise it was, how it threaded its way past Mars, Venus, Jupiter, and then disappeared behind the sun, as if following a path laid out long ago. Its orbit was the next mystery to unfold, too precise, too deliberate, almost rehearsed. You see, most visitors from interstellar space arrive at awkward angles, cutting through the solar system's plane like wayward stones skipping across a pond. They come from above or below the ecliptic, their paths tilted by tens of degrees, because the stars of our galaxy are scattered in all directions. But 3i Atlas was different. It entered the solar system as though it had been here before, travelling along a path nearly aligned with the very plane in which our planets move. Its inclination was barely 5 degrees off the ecliptic. Statistically, that's extraordinary. For an object born light years away to approach our system at that angle, the odds are so small they nearly vanish into nothingness. And yet, there it was, moving with a composure that felt almost purposeful. From the outer dark, it drifted inward, gliding past Jupiter's broad domain, then tracing a line that brought it close to Mars, closer still to Venus, before vanishing behind the sun precisely on the day of its perihelion, the moment when it was nearest to that great furnace of light. The timing was exquisite. Not a day early, not a day late. In celestial mechanics, precision is everything, and this level of precision was unsettling. Now, perhaps that sounds dramatic, but imagine standing in an observatory, late at night, watching the data points appear on your screen. You plot them, expecting a random scatter, and instead the points form a perfect curve, a curve that threads itself through the solar system like a needle through fabric. You would pause, wouldn't you? Because the universe, for all its beauty, is messy. Dust, perturbations, gravitational nudges, these things conspire to create chaos. Yet here was order. Astronomers began running simulations. They asked, What are the odds that an interstellar object would pass through the solar system with an inclination of less than 10 degrees relative to the ecliptic? The answer, depending on assumptions, was roughly 1 in several 100,000. Add to that the alignment with the orbits of 3 major planets, and the probability dropped further. It was, as one researcher put it, like tossing a coin 1,000 times and getting heads every single time. But science is cautious. Coincidences, however improbable, do happen. The galaxy is vast, billions of years allow for rare events, and yet the feeling persisted that this particular alignment meant something. The solar system, as seen from above, is a vast spinning disk. For an interstellar traveler to enter that disk, almost flat, to thread itself through the gravitational zones of multiple planets without disruption, and to emerge unscathed behind the sun, is something that demands explanation. You might remember Oumuamua, the first known interstellar visitor. Its path was steeply inclined about 123 degrees relative to the ecliptic. It plunged through our system like a spear, tumbling erratically, reflecting sunlight in flashes that made it seem to blink. Then there was Borisov, the second. That one behaved much more like a comet, but its inclination was again high, about 44 degrees. They came from random directions, as interstellar bodies should. But 3I, Atlas, well, it seemed to obey the geometry of our own celestial family. Some astronomers proposed that gravitational focusing might explain part of this. The combined pull of the Sun and the giant planets could subtly redirect incoming objects, bending their paths toward the ecliptic plane. Over millions of years, they argued, this bias might make aligned trajectories more common than pure statistics would suggest. And that's reasonable, to a point. But even gravitational focusing cannot easily explain the chain of near encounters 3I Atlas made, skimming the orbital zones of Mars, Venus, and Jupiter, one after the other, as though each planet's gravity had been penciled into the itinerary. When NASA's Jet Propulsion Laboratory released the preliminary orbital elements, the numbers were almost poetic. The object's perihelion distance, its closest approach to the Sun, was about 0.38 astronomical units, nearly the same as Mercury's orbit. Its eccentricity was immense, nearly 2.7, confirming its interstellar origin. But what drew the most attention was the longitude of the ascending node and the argument of perihelion, values that placed its path nearly flush with the solar system's main plane. It's easy, I suppose, to romanticize this sort of thing, to imagine a lonely traveler threading the ancient orbits of our planets, performing a dance choreographed by cosmic chance. Yet, when too many coincidences stack upon one another, the scientific mind grows restless. The universe, after all, is built on probability, and when probability begins to whisper, impossible, something deeper may be at play. Let's think about the forces shaping such an orbit. A true interstellar object moves through the galaxy under the gravitational influence of the Milky Way's vast disk. It might pass near other stars, feel their subtle tugs, and be deflected slightly each time. Over billions of years, these nudges add up, changing its trajectory in ways that seem random to us. To align so precisely with the solar system's ecliptic would require either immense coincidence or a path sculpted by gravitational interactions on a scale we do not yet understand. Some theorists began to wonder whether the Sun itself, moving through the galactic environment, could act as a collector of certain orbital angles. Imagine invisible currents of dust and debris sweeping along the galactic plane, like schools of fish following thermal flows in an ocean. As the solar system drifts through these regions, it might occasionally capture material moving in near-parallel trajectories. If 3I Atlas were part of such a current, then perhaps its path was not unique, but part of a pattern we've only just begun to glimpse. Still, the behavior of the object near the inner planets unsettled many. When it passed Mars, the alignment was nearly perfect, close enough that the Mars Reconnaissance Orbiter could have imaged it, though no data were released. Then it crossed the orbit of Venus, just days before vanishing into the glare of the Sunday timing so exact that it seemed almost scripted. And when, later, astronomers realized that the date of perihelion coincided precisely with its solar conjunction, the moment it disappeared behind the Sun, they couldn't help but raise their eyebrows. Because you see, Orbital dynamics are not choreographed by intention, but by momentum and chance. And yet, 3I Atlas behaved as though following a line drawn long ago, one that cut cleanly through the heart of the solar system. For many scientists, that was enough to merit closer scrutiny. Others, more cautious, warned against reading meaning into randomness. Still, the debate grew. I suppose what fascinates me most is not whether the orbit was planned or accidental, but what it reveals about the architecture of the solar system itself. When an interstellar object moves along the ecliptic, it interacts gravitationally with the planets in ways that amplify tiny differences. Its path becomes a mirror for our own cosmic geometry, reflecting the delicate balance of forces that keeps Earth where it is. In studying 3I Atlas, we were, in a sense, studying ourselves, the fragile precision of our place in the cosmic order. To put it simply, this orbit was too neat to ignore, and yet too mysterious to claim as evidence of anything beyond physics. That's the tension that defines good science, the space between wonder and skepticism. There's another aspect to consider: the object's velocity relative to the Sunday. For an interstellar traveler, its incoming speed was unusually modest, about 32 kilometers per second. That's faster than anything bound to the Sun, of course, but slower than expected for something plunging through from the galactic field. If its speed had been just a little lower, it might have been captured, becoming a permanent resident of our solar system. That near miss added another layer of improbability. A little slower, and it would have stayed. A little faster, and it would have passed far above the plane. But instead, it entered the narrow window in between the cosmic equivalent of threading a needle in a hurricane. What are we to make of this? Perhaps it was simply the universe being extravagant, as it so often is. Or perhaps our understanding of interstellar dynamics is still incomplete. There may be unseen influences, tidal currents in the galactic potential, or magnetic interactions between stellar winds that subtly guide these wanderers. If that's true, then 3I Atlas might be our first tangible clue to the hidden choreography of the galaxy. Comparing its orbit to those of Oumuamua and Borisov only deepens the intrigue. Oumuamua arrived steep, fast, uncooperative, its light curve tumbling in unpredictable ways. Borisov came in at a cleaner, comet-like angle, shedding dust and gas as if to reassure us it was ordinary. But 3I Atlas, well, it seemed to merge their contradictions: interstellar yet steady, alien yet familiar, chaotic yet symmetrical. And this symmetry, that's what draws the eye. The way its trajectory curved inward, brushed against the gravitational fields of our planets, and then disappeared behind the sun, was like a signature in motion, a pattern that didn't quite belong to randomness. You can almost imagine, if you let your thoughts drift far enough, that the universe itself was writing something across the sky, a phrase in a language we don't yet understand. But in science, imagination is both a gift and a danger. It drives discovery, but it can also seduce us into seeing intention where there is only chance. So astronomers returned to the data, recalculated the orbital solutions, and looked again. The numbers held, the precision remained. And that, paradoxically, was the most haunting thing of all, because if coincidence alone produced this alignment, then the universe is capable of organizing beauty through pure mathematics. And if something more shaped, it's some deeper gravitational order or physical bias, then perhaps our notion of randomness in interstellar motion needs rewriting. Either way, 3I Atlas was teaching us something profound, that the boundaries between chaos and design are thinner than we like to think. As it slipped closer to the sun, its tail lengthened, its glow intensified, and observers prepared for the next phase of the mystery. They would soon notice that its behavior defied one of the simplest rules of cometary physics, as though the universe had decided to break its own symmetry, turning the logic of sunlight and dust on its head. And that's where things began to unravel, or perhaps to reveal themselves. For as 3I Atlas drew closer to the sun, its behavior betrayed one of the oldest and simplest rules in celestial physics. Every comet, every icy wanderer we have ever studied, forms its tail in response to sunlight. The heat from the star vaporizes ices within the nucleus, and the solar wind streams of charged particles blows the released dust and gas away from the Sunday. It is a dance of light and pressure, of radiation and motion, and it always points outward, always. The sun pushes, the comet yields. But with 3I Atlas, something strange occurred. For several weeks, as it approached perihelion, astronomers observed jets of material not fleeing from the sun, but streaming toward it. You can imagine the confusion. Telescopes from Chile, from Hawaii, from orbital observatories all reported the same anomaly. Plumes of dust and gas curving inward, as if pulled rather than pushed. It was subtle at first, barely noticeable against the glare of the solar corona, but as days passed, the pattern grew undeniable. The tail bent toward the Sunday. Now, to understand how impossible that is, we have to recall what forces govern these delicate structures. Radiation pressure acts like a wind, sweeping fine dust outward. Magnetic fields can twist them slightly, but never invert them entirely. For the tail to point sunward, something within 3I Atlas had to be propelling matter in the opposite direction, as though the comet were, in some strange way, alive, actively controlling its own outflow. Scientists, of course, resisted such thoughts. The explanations began to stack up. Perhaps the shape of the nucleus was irregular, spinning in a way that directed jets inward for brief moments. Or maybe the apparent inversion was an illusion, a trick of perspective caused by our line of sight as the object moved behind the Sunday. But these explanations, well, they strained, under the weight of the data. The effect lasted too long, remained too consistent. It wasn't a glitch of geometry, it was something real, and that raised uncomfortable questions. Could electromagnetic forces within the plasma of the solar wind be bending the ejected particles back toward the sun? Some proposed that as a possible mechanism. After all, space is not empty, it's filled with charged particles and magnetic currents. If 3I Atlas carried a strong intrinsic magnetic field, perhaps generated by a metallic core rich in nickel, it might interact with the solar wind in unexpected ways. In that case, the tail's reversal would not violate physics, only our assumptions. But then came another surprise. Spectroscopic measurements of the jet material revealed a peculiar composition, traces of nickel vapor, again, but also an absence of water, and carbon compounds typically abundant in cometary outgassing. The ratio was all wrong. Ordinary comets are made mostly of ice, perhaps, 70 or 80%, with dust and rock making up the rest. But 3I Atlas appeared dry, almost metallic. To produce visible jets under those conditions, the heating would need to reach temperatures far beyond those that simple sunlight could provide. So, what was driving it? One hypothesis suggested sublimation of exotic materials, perhaps volatile metals or trapped gases deep within the structure, releasing energy as they transitioned between states. Another proposed piezoelectric effects, stress within the crystalline lattice, generating localized discharges as the object spun. Yet even these theories only explained fragments of the behavior. None could fully account for the sustained emission directed toward the Sunday. You see, in physics, when something resists explanation, we look for context. We compare, we contrast, we ask, has anything like this ever been observed before? The answer, in this case, was no. No comet in the recorded history of astronomy had ever consistently produced a sunward tail. The phenomenon was unprecedented, and so, the conversation shifted from what we could explain to what we could infer. If 3I Atlas was emitting material toward the sun, then some internal mechanism was influencing that directionality. Perhaps the rotation axis was aligned in such a way that, as it spun, it ejected matter preferentially along a vector that, by coincidence, pointed sunward. That would require a rotation period synchronized almost perfectly with its orbital velocity, a cosmic coincidence of the highest order. But coincidences, as we've already learned, seem to follow this object like shadows. Every property, every motion, every anomaly added another layer to the improbable. And yet, it was real, visible through telescopes, measurable, undeniable. Some astrophysicists began to speculate that we were witnessing a form of venting caused by internal reactivity. Imagine, if you will, a hollow structure beneath the surface pockets of trapped gases compressed over eons. As the sun's heat penetrated, those pockets could rupture, releasing jets of material in unexpected directions. The result might mimic control, when in fact it was chaos sculpted by deep time. Still, others weren't satisfied. They noted that the timing of these emissions seemed too consistent to be random. Each burst aligned with specific points in the object's rotation cycle, suggesting a periodic behavior. It was almost rhythmic, like breathing. And that rhythm, steady, recurring, made some whisper comparisons to engineered systems, though no credible scientist would make that leap publicly. You know, perhaps the most haunting part of this story is not the anomaly itself, but how quiet it was. The universe didn't shout its mysteries at us. It whispered them in the faint bending of light, in the subtle curvature of dust. The reverse tail of 3I Atlas wasn't dramatic in the cinematic sense. It was delicate, a slow-motion defiance of expectation. But in that defiance, it forced us to reconsider one of the most fundamental relationships in solar physics: the dialogue between light and matter. When sunlight meets a comet, it is supposed to dominate, to dictate, yet here was a fragment of another world pushing back, however slightly, as though asserting some ancient will of its own. Eventually, of course, as the weeks passed and the object receded from the sun, the anomaly faded. The tail straightened, returned to its expected orientation, and the chatter in observatories softened. Some claimed vindication proof that the earlier reversal had been an artifact of observation. Others held that the shift itself was evidence of a temporary process within the object, now spent. Whatever the truth, the fact remained that, for nearly a month, a comet, or what we thought was a comet, had broken the most reliable rule in the book. But what if that rule had never been as absolute as we believed? The solar wind, though constant on average, fluctuates with solar activity. Magnetic storms, coronal mass ejections, high-speed streams, they can twist and distort the local environment in complex ways. It's possible, though unlikely, that a surge of magnetic pressure during that period bent the ion tail inward. The timing of solar events that month did coincide with an unusual sequence of flares. Still, the geometry didn't quite fit. I suppose that's the essence of this mystery. It's not that we lack explanations, but that none fit completely. Each hypothesis solves one part and breaks another, like an equation balanced on one side but collapsing on the other. And in that imbalance lies the invitation to wonder. Imagine looking at the photographs, the faint bluish plume curling toward the sun, like a strand of smoke drawn inward, instead of blown away. There's something almost poetic in that inversion. As though 3I Atlas, born in the depths of interstellar night, was drawn not by repulsion but by attraction, seeking the very heart of the system that would soon burn it. It makes you think, doesn't it, about how even in the most predictable patterns of the cosmos, there are moments of rebellion, tiny gestures that remind us the universe is not bound by our comfort. It behaves as it will, and we are left to interpret. When data from the Hubble Space Telescope finally came through, the spectral signatures showed brief bursts of high-temperature emissions inconsistent with sunlight alone. That suggested either localized heating or a reaction occurring within the material itself. Some even speculated about low-level radioactive decay, perhaps residual isotopes from the era of its birth, releasing just enough energy to power jets from beneath its crust. If so, it would mean that this fragment carried within it not only the memory of a dead planet, but the slow heartbeat of its core, still pulsing after 10 billion years. The image of that, a piece of world long gone, whispering back to the sun through faint breaths of nickel vapor, has a kind of tragic beauty to it, and yet, in scientific terms, it points to something tangible: internal heat. Perhaps that's all it ever was, a simple expression of thermodynamics, made extraordinary only by our perspective. But there's one more detail that continues to trouble the models. During the period of the reverse tail, 3I Atlas showed minor fluctuations in brightness, regular as clockwork. Each pulse coincided with the release of new material. That suggests a rotational period of about 9 hours, far faster than expected for an object of its estimated size. A spin that rapid should tear it apart, unless its structure were exceptionally strong. Not porous ice, then, but dense, metallic, cohesive. In other words, exactly what earlier spectral readings implied. And if that's true, we are looking at something extraordinary. A survivor of cosmic violence, forged in the mantle of a destroyed world, spinning still after 10 billion years, and somehow, impossibly, resisting the forces that should have reduced it to dust. You see, the universe is full of such contradictions. It gives us rules, and then it breaks them. It invites us to understand, then reminds us how little we truly know. 3. Atlas's reverse tail was not merely a curiosity, it was a quiet rebellion against our assumptions, a message written in ionized gas and sunlight. As the object continued its journey outward, its emissions normalized, but the questions it left behind did not. What kind of structure could survive such rapid rotation without fracturing? What kind of internal energy could sustain those jets for weeks? And perhaps, most puzzling of all, why did it choose that moment, its closest approach to the Sun, to behave in a way no natural comet ever had? The telescopes kept watching, of course, hungry for new data, and as the tail settled, the attention of astronomers turned to something else, something equally perplexing. The chemical fingerprints of 3I Atlas did not belong to any cometary family we had catalogued. Its spectrum was too rich in nickel, too poor in water, too alien to fit. And so, as it drifted away from the Sun, the focus shifted from its motion to its matter, from how it moved to what it was made of. What came next was, perhaps, even more unsettling than the reverse tail. When the object emerged from behind the Sun, and the instruments could once again capture its light, astronomers began dissecting its spectrum, the unique fingerprint of elements that reveal what something is made of. It's one of the simplest and yet most profound tools we have. By splitting light into its component wavelengths, we can read the story of matter itself, the gases that burn, the metals that shimmer, the molecules that sing in the darkness. And yet, the story 3I Atlas told was not the one anyone expected. You see, comets are meant to be simple things, dirty. Snowballs, mostly ice laced with dust and rock, relics of early solar systems. When sunlight hits them, the ice sublimates, releasing water vapor, carbon dioxide, ammonia, and other volatiles. The result is a spectrum dominated by those familiar molecular bands. But when astronomers analyzed 3I Atlas, those expected signatures were almost absent. Instead, they found strong metallic lines, nickel, chromium, traces of magnesium, and astonishingly little water. Only about 4% of its surface emissions could be attributed to H2O. Compare that to the 70 or 80% typical of any ordinary comet, even interstellar ones like Borisov. The numbers didn't add up. This was not a block of frozen gas. It was something dense, cohesive, forged under pressures far beyond what loose dust and ice could endure. And the presence of nickel in such quantities was particularly strange. Nickel is forged deep within planets, under immense heat and gravity. It doesn't survive near the surface of icy comets. It belongs to cores, to the hearts of worlds. That realization sent a shiver through the scientific community. Because if this was truly a fragment of a planetary core, then we were not just looking at a comet from another star. We were looking at a fossil from the interior of a world that no longer exists. Perhaps, billions of years ago, its parent planet was torn apart by a collision, or by the death throes of its sun, and this fragment, this shard of nickel and rock, was hurled into interstellar space. And there it wandered, for 10 billion years, a survivor of destruction, a memory of creation. Now, well, that's an extraordinary thought. Imagine holding a pebble that once lay near the core of a world born before the solar system itself. Imagine that it drifted through the Milky Way for longer than life has existed on Earth, gathering cosmic dust, scarred by radiation, until one day it passed close enough to our sun to catch its light. That's not science fiction. That's the quiet poetry of the cosmos made real. Spectroscopy, though, is a precise language, and its grammar leaves little room for metaphor. The data revealed a specific pattern, strong emission lines from ionized nickel at wavelengths around 340 and 360 nanometers, weaker lines from iron, and an almost complete absence of water's broad molecular bands. There were also faint hints of silicon and magnesium oxides materials found in rocky mantles rather than icy exteriors. In short, 3I Atlas looked less like a comet and more like an asteroid core, or perhaps a fragment of a differentiated planet, where gravity had already separated the metals from the silicates long ago. That finding alone was enough to rewrite textbooks, but then came the question of stability. How could such a metallic object survive the violent heating near the sun without melting or breaking apart? Ordinary comets disintegrate under those conditions. Borisov, for example, fragmented rapidly during its approach. Yet 3I Atlas endured. Its brightness fluctuated, yes, but it did not shatter. It held together, as though it were forged of something far stronger than ice and dust. Some researchers proposed that this resilience came from its structure, a dense lattice of nickel and silicate, fused by cosmic radiation over eons. Others suggested that internal pressure, frozen in when the object first cooled, acted like a structural skeleton, maintaining integrity even under solar stress. Whatever the cause, its survival defied expectation. When scientists compared its chemical profile to Borisov, the differences were stark. Borisov's spectrum was textbook: water vapor, cyanide, diatomic carbon, the fingerprints of a traditional comet from another star. 3I Atlas, by contrast, seemed alien. If Borisov was a message from a familiar type of planetary nursery, 3I Atlas was a whisper from something older, more exotic. Perhaps, some mused, we were seeing not the product of a star like our Sun, but of one very different, maybe a massive, short-lived star whose planets condensed from metal-rich debris. In such an environment, ices would be rare, metals abundant. The resulting bodies would be rocky, heavy, enduring, and if one of them were torn apart, its fragments could wander the galaxy for eons, outlasting even their parent stars. There's a beautiful irony in that thought, that the death of one system might cast seeds into space, and one of those seeds would, one day, drift through ours. The universe recycles everything, even its catastrophes. Still, the nickel lines troubled many. Not just their intensity, but their consistency. Over several weeks of observation, as the object receded from the sun, the nickel emissions remained stable, even as the temperature should have dropped. In ordinary cases, volatile materials sublimate quickly and fade. But here, the lines persisted, suggesting that nickel wasn't just on the surface, it was throughout. The entire body might be saturated with it. And here's the most curious part. The ratio of nickel to iron was inverted compared to what we see on Earth. Normally, iron dominates by a wide margin. But in 3I Atlas, nickel was several times more abundant. That's almost unheard of in natural processes. Iron forms more readily in stellar nucleosynthesis. Nickel requires higher energies and specific conditions. Its abundance implied an origin in a stellar environment, quite unlike our own, perhaps near a supernova remnant, or in the heart of an early galaxy, where heavy element production followed different pathways. So, what was this thing? Not a comet, not an asteroid, at least not in the conventional sense. Something in between a relic of a time when planetary formation itself was a rougher, stranger process. I suppose, that's what makes it so humbling. We often think of our solar system as the standard, the template. But 3I Atlas reminds us that there is no standard, only variations, countless experiments in cosmic architecture, each leaving behind its debris. And when such a fragment passes through our sky, it's like opening a window into another laboratory of creation. Some tried to build a conservative model to fit all the observations. In that model, 3I Atlas began its life as part of a large, metal-rich planet orbiting a star several times older than the Sunday. When that star aged and expanded, it stripped away the planet's outer layers. Later, perhaps during a gravitational encounter, the planet was torn apart, flinging pieces into interstellar space. One of those pieces, containing the dense core, began a long voyage through the galaxy. Over billions of years, radiation hardened its surface, sealing it in a shell of nickel oxide. Inside, radioactive decay continued slow, steady, providing just enough internal heat to keep it intact, and, perhaps, to drive the faint jets we observed near the Sunday. In that sense, its strange behavior would not be mystical but purely physical, the dying heartbeat of a planetary relic. It's a compelling idea because it requires no miracles, only patience and time, the quantities the universe has in abundance. and it fits the data neatly enough to satisfy the scientific mind, though not completely. The same model, for instance, struggles to explain the lack of other metals like cobalt and manganese, which should accompany nickel if the object truly came from a planetary mantle. That inconsistency leaves the door open for more exotic interpretations. But before leaping into speculation, one must appreciate what the conservative model already implies. If 3I Atlas really is a planetary fragment from a system 10 billion years older than ours, then its existence changes how we think about interstellar debris. It means that some planetary remnants can survive nearly the entire age of the galaxy. It means that our solar system may, from time to time, be visited by the literal fossils of worlds long dead, and it means that, buried in their spectra, are records of stellar chemistry and planetary processes that predate our Sunday. That's extraordinary, because it turns astronomy into archaeology on a cosmic scale. We are not just observing objects, we are excavating them, digging through the layers of the universe's past, one fragment at a time. There's also a philosophical beauty to it, the idea that even destruction leaves creation in its wake, that every collision, every supernova, every gravitational rift sends echoes into the future in the form of matter that remembers, and when one of those echoes crosses our sky, it invites us to listen. Still, the persistence of the nickel signature wasn't the end of the mystery. As the object moved farther from the sun, its overall brightness began to change in a way that didn't match its distance. Normally, a comet dims predictably as it recedes, following an inverse square law with sunlight, but 3I Atlas didn't fade evenly. Its luminosity oscillated, as though something beneath its surface continued to stir. This periodic brightening hinted at ongoing processes, chemical perhaps, or even radioactive. That's where the idea of internal heat resurfaced. The decay of nickel isotopes can produce significant energy, especially in dense bodies. If 3I Atlas retained enough of that material, it could maintain internal temperatures high enough to sustain emission lines for weeks or months after its solar encounter. And that possibility, mundane as it might sound, carries implications that border on the profound. Because if a fragment like this can remain thermally active for billions of years, then interstellar space is not as dead as we once thought. It's filled with slow fires, ancient embers glowing in the dark, keeping the memory of lost worlds alive. The story of 3I Atlas, then, is not merely about composition or chemistry. It's about endurance, about the stubborn persistence of matter against entropy, about how something forged in the furnace of a forgotten star can cross the cold gulf of time and still, when it meets the sun, whisper back in light. And yet, just when the data began to settle into patterns, when scientists thought they could finally define its nature, the object changed again. After its closest approach, as it moved outward, its color began to shift. Observers noted a strange hue creeping into its spectrum, a bluish radiance, more intense than before, so vivid that even amateur astronomers remarked upon it. And that hue, inexplicably, was bluer than the sun itself. And then, just when scientists began to believe they understood it, 3I Atlas changed again. The color of its light, its very tone shifted toward the impossible. As it re-emerged from behind the sun, telescopes across the world captured a glow so vivid, so defiantly blue, that for a brief moment it outshone the sun itself in hue. Not in brightness, of course, but in temperature of color. It was as if the cold heart of the cosmos had been heated to a purity that mocked the golden warmth of our star. At first, it seemed like an error. Instruments can mislead when dealing with objects so close to the sun's glare, but independent confirmations came quickly from Chile, from the Canary Islands, from the Lunar Gateway spectrograph. The wavelength readings were clear. The emission peak had moved upward toward the high-energy end of the visible spectrum. To appear bluer than the sun means something profoundly simple, yet staggering. The source must be hotter. But how could a fragment of rock, even one as strange as this, radiate at a temperature exceeding the sun's surface? You see, this was not the soft cyan of cometary gases, the fluorescence of carbon molecules reacting to sunlight. This was something else, sharper, cleaner, closer to the spectrum of heated metal. It was as if 3I Atlas, in that moment of emergence, was not reflecting light but generating it. And that, well, was not supposed to happen. Comets shine by borrowed light. They do not burn. They cannot. There are moments in science that feel like the universe clearing its throat, reminding us we're still students. This was one of them. Some astronomers suggested the color shift was due to scattering fine metallic dust, refracting sunlight differently, as viewing angles changed. Others proposed plasma interactions near the sun's magnetic field, which might energize certain ions and produce blue emission lines, but neither explanation matched the data fully. The light curve showed not just a change in color, but an increase in intensity, brief, sudden, and then steady again. For a few hours, it seemed that the object had undergone a kind of ignition, a controlled burst of heat from within, visible across millions of kilometers, and then, quietly, it subsided. Whatever happened behind the sun, during those days when no telescope could see, had altered it. To understand how, strange that is, imagine heating a rock until it glows. At 2000 degrees, it turns dull red. At 3000, orange. At 5000, it approaches white. To reach the blue-white hue recorded by observatories, its surface or something within its coma would need to exceed 6000 Kelvin, hotter than the photosphere of the sun itself. That's not sunlight reflected, that's energy released. Some whispered about chemical reactions, exothermic decompositions of trapped compounds exposed to sudden solar heat. Others mentioned radioactivity, the slow decay of heavy isotopes accumulated over billions of years, perhaps momentarily accelerated by solar radiation. But to emit that much light in so short a time would require an immense release of energy. Not an explosion, not a flare, but a controlled surge like a deep exhalation from the object's heart. You might say, well, perhaps we're romanticizing it. Perhaps the light was only an illusion, a trick of angle, a transient alignment of reflective facets. But spectroscopy doesn't romanticize. It records wavelengths, and those don't lie. The peaks told a story of genuine thermal emission, not mere reflection. There is a quiet terror in that realization, the way a single observation can undo decades of certainty. Because if an interstellar fragment can generate heat beyond what sunlight alone provides, then our understanding of inert matter in deep space is incomplete. Something within 3I Atlas was active, however briefly. Not alive, of course, but responsive, as though the encounter with the sun awakened a dormant process, one that had been waiting for warmth for 10 billion years. And that's the thing, you see. We tend to think of space as static. Rocks are rocks, cold and dead. But perhaps the universe is more patient than we imagine. Perhaps energy can hide for ages in the lattice of matter, locked in by pressure and time, waiting for the right alignment to whisper its presence again. Some proposed an elegant possibility. As 3I Atlas passed behind the sun, it might have absorbed an enormous flux of solar particles, charging its metallic surface. When it emerged, that energy could have been released through photoelectric emission, giving rise to the brief blue radiance. The idea is tantalizing because it bridges physics and poetry, the notion of a relic of another world being momentarily rekindled by our star's breath. Still, that explanation doesn't account for the symmetry of the event. The glow wasn't localized. It enveloped the entire coma, as though the object's entire surface responded in unison. That implies a coordinated structure beneath the crust, a network of conductive channels or veins capable of distributing charge evenly. Which, in turn, suggests that this wasn't just a lump of rock and metal. It was structured. The realization unsettled many scientists. A naturally occurring lattice capable of conducting and releasing energy across the entire body is theoretically possible, but extremely rare. It would require a combination of nickel alloys, crystalline silicates, and carbon inclusions formed under immense pressure. If such a configuration existed, it could explain not only the uniform blue glow, but also the object's previous anomalies, its sunward jets, its stability near perihelion, its resistance to disintegration. In that sense, the mystery began to resolve into a pattern. 3I Atlas, as a relic core, dense and coherent, perhaps even partially crystalline, its metallic composition allowing it to store and release energy in ways ordinary comets cannot. The blueness, then, would not be a miracle, merely a revelation, of what deep time can create when it's given 10 billion years to work. But the poetic mind resists mere equations. There was something eerily beautiful about that light. Amateur astronomers described it as electric, like the shimmer of arc plasma. Some said it reminded them of lightning, frozen in time. Others, of the brief, perfect blue that flashes when a meteor breaks apart high in Earth's atmosphere. It was, in every sense, unnatural to our expectations, yet profoundly natural to the cosmos that birthed it. And perhaps that's the lesson here. The universe does not care about what we think should be possible. It simply expresses itself. When the data reached the public archives, the debate turned almost philosophical. Was this the moment we should admit that our models of cometary physics were incomplete? Or was it simply another example of how observation outpaces theory? The community divided gently, as scientists often do, half insisting on patience, half whispering that something fundamental had been missed. The timing of the event didn't help. The blue phase occurred during a period when several solar observatories, including those of NASA and the Chinese National Space Administration, experienced temporary data dropouts due to solar interference. It was as if nature had conspired to conceal the precise moment of transformation. What exactly happened behind the sun remains undocumented, a gap in the record that no telescope can fill. And so, speculation thrives in the shadows. Some suggest that intense solar magnetism might have induced eddy currents in the metallic body, heating it from within. Others wonder whether the sudden blueness was the outward symptom of internal stress, a partial melting of its crust, exposing fresh, reflective surfaces. Both ideas fit pieces of the puzzle, yet neither fits the whole. I suppose that's what makes 3I Atlas so compelling. It sits in that narrow band between understanding and awe. We can model parts of its behavior, simulate its heat curves, plot its spectral peaks, but somewhere beneath those numbers lies a mystery that refuses to yield. And perhaps that's as it should be. Because when you stare at something that glows bluer than the sun, you can't help but feel a kind of reverence. You're not just seeing chemistry, you're seeing the memory of creation itself, briefly reignited. That light, after all, travelled to us across 93 million miles, carrying the story of an object that had travelled billions of years to tell it. And there's a strange intimacy in that exchange. The sun, ancient and familiar, meeting an even older traveller, their energies touching for a fleeting instant, two histories crossing paths, leaving behind a signature of light no one can quite explain. Eventually, as the days passed, the object dimmed again. The blue faded, replaced by the duller grey of a cooling ember. But it left behind questions that refused to cool. If the colour shift was a natural consequence of its composition, then our understanding of interstellar chemistry is incomplete. If it was not, then something else, something we haven't named, was at play. In the end, it doesn't matter which explanation is true, because both are extraordinary. Either the laws of physics are broader than we thought, or the universe just performed an experiment before our eyes that we haven't yet learned how to read. What happened behind the sun changed 3I Atlas forever. And yet, as it moved outward once more, it carried the evidence of that encounter within its light, a signature no one could quite decipher. The telescopes followed, their instruments hungry for clues, and soon the story would shift from the light it emitted to the silence it entered. Because in the weeks that followed, as the blue faded and the data streams flickered, gaps began to appear in the records, blank intervals where observation ceased and mystery began. And then, quite suddenly, the sky went silent. For days after its radiant blue awakening, as 3I Atlas continued along its outbound path, astronomers around the world noticed something strange, not in the comet itself, but in the record of it. The data feeds began to thin out. First came a delay from the Mars Reconnaissance Orbiter, which was scheduled to capture a high-resolution sequence of the object as it passed near Mars's orbit on the 2nd of October. The images never arrived. Then, from the Chinese observatory at Purple Mountain Tucson, there was an absence, too. Their instruments, capable of ultraviolet spectroscopy, had been tracking 3I Atlas before it slipped behind the Sunday. When it emerged, their public data logs went dark for nearly a week. Now, it's tempting to see patterns where there might be none. Space agencies handle vast amounts of information, and transmission delays are common. But the timing, oh, The timing could not have been more peculiar. Just as the object performed its most inexplicable act, brightening to an unnatural blue and reappearing from behind the sun, our collective vision dimmed. There was a gap, a blank chapter in the cosmic story. And in science, absence can be as evocative as presence. The missing data triggered a quiet storm within the far astronomical community. Forums filled with speculation. Had there been a failure in the satellite's sensors? A prioritization shift towards solar flare monitoring? Or, as some whispered, a decision, intentional or not, to hold the images for internal review? You see, astronomy isn't as free from politics as we'd like to believe. Behind every telescope, there's a country, a budget, a network of permissions, and when the universe performs something rare, information can become currency. Still, I don't think it was conspiracy. More likely, it was bureaucracy meeting wonder. The reality of space observation in 2025 is that every discovery must pass through filters, data integrity, security, classification, even national interest. Some satellites are dual use, serving both science and defense. Others share transmission bandwidth with critical systems. When something unexpected happens, the lines between curiosity and caution blur. But, well, to those waiting for the numbers, it felt personal. The cosmos had offered us a mystery, and suddenly, the instruments designed to interpret it went quiet. It's a bit like standing before a painting when the lights go out. You know beauty is there, but you can only sense its outline. NASA's official explanation came days later. A temporary data backlog due to solar interference and hardware calibration. Reasonable and likely true. Yet the Chinese observatory issued no comment at all, leaving a gap of silence that was quickly filled by speculation. Amateur astronomers, working from ground-based observatories, tried to bridge the void with their own readings, but near the sun's glare, their instruments were blinded. The result was an eerie pause in the record, a curtain drawn just as the act reached its climax. And perhaps that's the lesson here. Not everything we wish to know can be known. Even with our best machines, the universe still keeps secrets. What makes this particular episode interesting is how it reveals the delicate interplay between science and the structures that support it. Astronomy depends on cooperation. No single nation can watch the whole sky. Data must be shared, cross-checked, combined. And yet, sharing always comes with hesitation. Knowledge, like territory, is something to be guarded. For decades, space exploration has walked that line. Satellites built for research ride atop rockets built for surveillance. Observatories funded by international coalitions must navigate the politics of access. Even a raw image of a comet, when captured by a spacecraft in orbit, may be routed through classified systems before scientists ever see it. And so, when gaps appear in the data stream, it's rarely because someone is hiding a secret about aliens or anomalies. It's because science, like everything human, moves at the speed of permission. You might say, well, that's frustrating. And it is. But it's also a reminder that discovery is not a pure act of imagination. It's a negotiation between curiosity and control. The universe speaks freely. We just don't always have the freedom to listen. In this case, the missing frames from Mars Reconnaissance Orbiter and Purple Mountain weren't just technical losses. They represented lost context. Without continuous imaging, we can't know exactly what 3I Atlas did during its perihelion. The point closest to the Sunday, did it fragment? Did it eject material in response to solar pressure? Did its brightness peak and then fade in minutes? We can only guess, interpolating from before and after. It's strange to think that something could happen right next to the Sun, visible in principle to half the telescopes in the solar system, and yet remain undocumented. But that's the reality of observation. The Sun blinds our eyes, both figuratively and literally, and what happens in its shadow often escapes the record. Still, scientists pressed on. They gathered what they could light, curves from observatories that caught the edges of the event, spectral echoes from instruments tuned to other frequencies, even radar data from passing spacecraft. Each fragment offered a clue, and yet, none of it replaced what was missing. When I think of that, I can't help but reflect on how fragile our window into the universe really is. All our technology, all our knowledge, And still we depend on moments of alignment between Earth and object, between time and sunlight, between nations willing to share what they see. It's a reminder that science, for all its grandeur, is an act of trust. The irony, of course, is that these gaps in data often generate more imagination than the data itself. Where information ends, story begins. The absence becomes a stage upon which possibility performs. Some speculated that the missing hours might conceal a breakup, a discharge of energy, perhaps even the release of some artificial emission. Others suggested that nothing unusual occurred at all, that the silence was simply the echo of administrative delay. The truth, perhaps, lies somewhere in between, the cosmos doing something subtle and magnificent, while humans argued over bandwidth. But beyond the surface intrigue, the incident revealed something deeper, the politics of knowledge. Space is no longer the frontier of lone dreamers with telescopes. It's an arena of nations, each with ambitions. Observing a rare interstellar visitor isn't just science, it's prestige, influence, proof of capability. When one agency releases a discovery, another might hesitate to confirm it too quickly, wary of lending weight to a rival's claim. In such a climate, even the flow of data becomes a performance of power. And yet, even with all the institutional tension, what drives these scientists remains remarkably pure. The desire to understand. That's what makes the silence so haunting. Not because it hints at conspiracy, but because it reminds us of the fragility of human cooperation in the face of cosmic wonder. In the end, most of the missing data did reappear. NASA's archives updated weeks later with partial imagery, and a few frames from the Chinese observatory were quietly included in an academic preprint. The images were blurred, incomplete but real, and they showed what we already suspected. At its closest approach, 3-eye Atlas brightened intensely, then dimmed, as if releasing something. A burst of light, a shedding of material perhaps, and then the quiet retreat into space. Still, the interval of absence remains. It is a hole in the record, a blank line in the poem of the cosmos. And that blankness invites humility, because for all our precision, the universe still chooses what to reveal. You see, science doesn't thrive on certainty, it thrives on the tension between what is seen and what is missing. When we look into those gaps, we see not failure, but opportunity. The gaps force us to think, to test, to doubt, to create better instruments and better models. And that, in a strange way, is how knowledge grows, by confronting its own darkness. When I talk to astronomers about this, they rarely sound frustrated. They sound contemplative. They know that every unanswered question is an invitation, not an obstacle. They live in that space between data and mystery, between politics and wonder, and somehow they make meaning of it. And that's what happened here. Out of those missing hours was born a deeper inquiry, not just into 3-eye Atlas, but into our own relationship with the unknown. How do we act when the evidence refuses to behave? How do we preserve objectivity when the data itself is incomplete? There's a certain elegance in that uncertainty. It reminds us that science isn't about possessing truth, but about pursuing it, endlessly, humbly. The universe hides far more than it shows, and we, in our short lifetimes, must learn to read between the lines. As the debate over the missing data quieted, attention turned once again to the object itself, to the meaning of those numbers that didn't quite fit, those models that refused to settle. Because when data gaps appear, one question always follows. Were the instruments at fault, or was reality? And that's where the story moves next to the question every scientist must face when the universe refuses to obey its own equations. When the gaps finally closed, and the world of astronomy began comparing notes, a quiet consensus formed not about what had happened, but about what could not be ignored. The data, fragmentary as it was, refused to fit into any existing model. It wasn't wrong exactly, it was simply inconvenient, like a truth that didn't care to make sense. And that left scientists standing at the edge of a familiar crossroads. Because when the universe stops cooperating, there are only 3 possibilities. The data is flawed, the model is flawed, or something genuinely new has emerged. You see, that's the rhythm of discovery. Every great leap in science begins with something that refuses to fit a small discord in an otherwise perfect melody. And 3. eye, Atlas, was a symphony of discord. The spectral lines didn't match known materials, the orbit was too precise to be random, the light was too blue, and the timing of its outburst too convenient. The simplest explanation was error. Perhaps the instruments misread, perhaps calibration slipped, perhaps the sun's interference corrupted the data. It's always tempting to blame the tools first. But this time, that explanation collapsed quickly. Because the readings came from too many independent sources, from telescopes on different continents, from spacecraft in orbit, from observatories governed by nations that rarely agree on anything. Yet all reported the same numbers. The blue shift was real, the metallic composition was real, the tail reversal, real. These were not mistakes. So, if the data was sound, then the next suspect was the model itself, the grand, elegant machinery of cometary physics that has served us for centuries. That model assumes that comets are fragile, icy remnants of early planetary formation, easily disrupted by solar heat, driven entirely by radiation pressure. It assumes that interstellar comets, though rare, behave roughly the same way. But 3I Atlas behaved like no comet ever known. It didn't crumble at perihelion, it didn't shed a predictable stream of volatiles, and it didn't fade as expected. It glowed hotter than the sun, then cooled as if exhaling. Perhaps, then, our understanding of interstellar bodies is incomplete. Perhaps the galaxy produces objects that don't fit the comet-asteroid dichotomy. After all, nature doesn't care for our categories. There may exist entire families of relics forged in different environments, planets that condensed from supernova debris, worlds born around dying stars, fragments of long-vanished systems that evolved under exotic pressures, and chemistries. And maybe, well, 3I Atlas was one of them, a member of a class we have yet to name. A new kind of traveller, bridging the line between metal and ice, between inert matter and something faintly reactive. If so, then its strange behaviour wasn't a violation of physics but an expansion of it. But there's also the third possibility, the one every scientist both fears and secretly hopes for, that we are witnessing a phenomenon entirely new, something unimagined. A process that has never before been observed because it rarely occurs, or because we've never been looking at the right moment. That's the dangerous idea, the one that can tempt you into romance if you're not careful. Because to say something new is to admit you no longer know where the ground lies. Still, it's hard not to wonder, what if the universe has ways of storing energy we don't yet understand? What if deep within the interstellar medium, far from any star, materials evolve in darkness, metastable, charged, waiting for a spark to awaken them? Then, when such an object passes near a sun, the heat doesn't destroy it but triggers something within, something like memory. It's speculative, yes, but so were most of physics before evidence caught up. The question is, how far one dares to stretch before the thread of science begins to fray into myth. And that's where the attitude of real science becomes vital. The temptation, of course, is to leap toward the extraordinary, to whisper of alien technology, of ancient probes, of purposeful design. The mind loves patterns, and 3I Atlas offered plenty. The perfect orbit, the metallic structure, the symmetrical emission. But science demands restraint. The more seductive the idea, the more skeptical we must become, because wonder, while beautiful, can cloud precision. Still, skepticism does not mean dismissal. It means curiosity held in check by discipline. The astronomers who studied 3I Atlas knew this well. They didn't mock the oddities, they documented them, mapped them, weighed them against known physics. The more they did, the clearer it became that something fundamental was missing in our understanding of how such bodies behave. Take the tail reversal, for instance. No known comet exhibits such sustained directional, outgassing toward the Sunday. But suppose the core of 3I Atlas was laced with magnetic metals, capable of interacting with the solar magnetic field. Suppose its internal structure allowed for a temporary alignment, an electromagnetic coupling that altered the trajectory of ionized dust. In that case, the tail's behavior could be explained not by mysticism, but by magnetohydrodynamics on an interstellar scale. The mechanism would still be remarkable, but not impossible. And yet, even that wouldn't explain the blue light. To emit radiation at those temperatures without disintegration implies a material with extraordinary thermal stability, perhaps a metal alloy, unknown in our solar system, forged under different cosmic conditions. Again, it doesn't violate physics. It simply widens the boundaries of what's possible. That's how science grows. Every time reality refuses to conform, the map expands, the models are revised, and the mystery becomes the foundation for a deeper order. But there was something else unsettling about 3I Atlas, something less about physics and more about probability, the coincidences. The nearly perfect orbital plane, the timing of its perihelion, aligning exactly with its disappearance behind the Sunday. The fact that, in a galaxy of 100 billion stars, one of the few interstellar visitors we've ever seen happened to thread its way precisely through the inner solar system, passing close to Mars, Venus, and Jupiter in sequence, like a needle sewing through orbits. Statistically, that should not happen often, and yet it did. You might say, well, randomness allows for miracles given enough time, and that's true. But this wasn't just a single coincidence, it was a chain. Each link, improbable on its own, yet all perfectly aligned. And when coincidences start to form patterns, the scientist's mind hesitates. Is it chance, or is it that our models of randomness are incomplete? The history of astronomy is filled with such moments. Uranus's orbit didn't match predictions, so we discovered Neptune. Mercury's motion defied Newton, so Einstein found relativity. Each anomaly was an invitation to see the cosmos more clearly. Perhaps 3I Atlas is another such invitation, a sign that our picture of interstellar dynamics lacks a vital dimension. It's easy to imagine the conversation in research rooms late at night. Teams staring at data projections, tracing orbital plots, arguing quietly over which of the three paths to follow. Was it faulty data, a flawed model, or an undiscovered phenomenon? There's a certain beauty in that tension, because it's the essence of human inquiry, the refusal to settle for ignorance, even when certainty slips away. Some leaned toward the cautious path, insisting that better measurements would restore order. Others, the bolder ones, whispered of an entirely new category of object planetary relics, imbued with energy processes unknown to us. And a few, though reluctant, began to wonder whether the probability of such alignments could truly be accidental. You can imagine the atmosphere curiosity tinged with unease. Because when nature begins to mimic intention, it stirs something deep in us. It reminds us that the line between pattern and purpose is thinner than we'd like to admit. But even in those whispers, the scientific ethos held firm. No leaps without evidence, no romance without rigor. For every extraordinary claim, extraordinary proof must follow. Until then, 3I Atlas remained what it was, a puzzle, a mirror reflecting both the precision of the cosmos and the limits of human understanding. And so, the work continued. Simulations ran for months, testing every conceivable combination of parameters. They tweaked the density, the spin rate, the albedo, the magnetic flux. Each iteration failed to reproduce the observed behavior fully. The object defied modeling, as though reminding us that the universe is under no obligation to be simple. Still, patterns began to emerge, subtle hints that the key might lie in its internal structure. A metallic lattice could account for its endurance, a low water content for its stability, a radioactive interior for its sustained emissions. Slowly, the outlines of a new natural explanation began to take shape, fragile and incomplete, but promising. It was a comforting idea, in a way that this was not a messenger from elsewhere, but a relic of natural law playing out under unfamiliar conditions. A planetary core, perhaps, from a system older and stranger than ours, torn from its home, flung into the dark, preserved by time and vacuum. That story fit. The data, mostly, but not all of it. The brightness remained too high, the spectral shift too extreme, the sequence of coincidences still unresolved. And yet, that's the beauty of science. It tolerates imperfection. It moves forward, not by closing doors, but by leaving them ajar. By the close of that year, most researchers had settled, cautiously, on a view. The data was solid, the model incomplete, and the phenomenon, while extraordinary, likely natural. But beneath the surface of that consensus ran a current of quiet curiosity, because even those who argued for a natural explanation couldn't deny that the odds were astonishing. And so, in conference halls and late-night discussions, one question lingered unspoken. If 3I Atlas was truly natural, then nature is far stranger, far more inventive than we've ever dared to imagine. That thought, half comfort, half revelation, would become the foundation of the next inquiry. Because if this visitor could behave in ways so improbable, yet so precise, then perhaps it was time to ask what kind of natural history could produce such perfection. And that question, in turn, would lead scientists toward the strongest natural hypothesis of all, the idea that 3I Atlas might not be a comet at all, but the indestructible heart of a planet that once lived, died, and left behind only its shining, ancient core. The theory that began to take shape was, in its simplicity, almost poetic. What if 3I Atlas was not a comet at all, but the fossilized heart of a world long dead, a planetary core, adrift in the darkness between stars? It explained so much. Its strength, its density, its metallic sheen, its refusal to crumble even when it ventured near the inferno of the Sunday. Unlike comets made of ice and dust, this object was solid, enduring, forged in the crucible of a planet's birth, and tempered by 10 billion years of wandering. You see, when a planet forms, it differentiates. The heavy metals sink inward, drawn by gravity, while the lighter materials rise to the surface. Iron, nickel, and other dense elements gather in the center, creating a molten heart. If that planet were later shattered by a collision, by its star's death, or by some gravitational upheaval, those cores could be flung into the void, stripped of their mantles, bare and gleaming. Over time, cosmic radiation would scar their surfaces, the cold of interstellar space would freeze them into silence, and they would become exactly what we saw that October, an ancient relic, polished by eternity. It was, perhaps, the most elegant of the natural explanations, because it required no miracles. Only time, and time, as we know, is the universe's greatest craftsman. The model fit the observations almost too perfectly. A metallic core, rich in nickel, could account for the strong spectral lines and the unusually high reflectivity. The lack of volatiles explained its resistance to sublimation. Its structural integrity made sense too. A dense, solid body could survive a close pass to the sun without fracturing, unlike a typical comet. Even the weak but persistent energy release could be explained by the slow radioactive decay of isotopes buried deep within. And that decay, tiny as it might be, could provide internal heat for billions of years. It would not melt the body, but it might maintain subtle thermal gradients enough to trigger the faint jets and emissions seen near perihelion. Those jets, emerging from microscopic fissures, could be directed by internal structure, producing the illusion of controlled outgassing. The mysterious blue glow, too, could arise from ionized nickel vapor, excited by solar radiation and magnetic fields. Every piece seemed to fit, or nearly so. The story that emerged was one of unimaginable endurance. Picture it, a planet forming around an ancient star, perhaps twice the age of our Sunday. For hundreds of millions of years, it circles quietly, its molten heart cooling, its crust thickening. Then, catastrophe, a collision with another planet, or the violent expansion of its parent star, tears it apart. The outer layers disperse into gas and dust, but the core remains, flung into space like a seed. It drifts through the galaxy for eons, slipping between stars, grazing the edges of nebulae, crossing spiral arms, gathering the dust of ages. Eventually, by chance alone, it approaches our solar system and, for a brief moment, meets our gaze. It's a humbling thought, isn't it? That what we saw may not be the beginning of a story, but its final echo. That the light which shimmered blue against the sun's fire was the afterglow of a world that lived and died before Earth ever existed. And yet, it's also oddly comforting, because it tells us that even in destruction, the universe preserves its memories. Nothing truly vanishes, it only changes form. The more the scientist looked, the more persuasive this theory became. It didn't require rewriting the laws of physics, only expanding their stage. The universe is vast enough and old enough for such survivors to exist. Statistically, there must be countless planetary remnants wandering the interstellar dark cores without shells, husks without orbits, ghosts of long-forgotten systems. 3. Atlas might simply be the first one we've seen clearly enough to recognize. Of course, simply is never simple. There were still problems, as there always are. The persistent brightness near perihelion was stronger than expected, even for a metallic surface. Some simulations suggested that if the object's surface were fractured into reflective planes, like facets of an enormous crystal, it could scatter sunlight more efficiently than any known asteroid. Others proposed that chemical reactions between solar wind ions and nickel compounds could have produced short-lived luminescence. None of these fully satisfied the data, but they carried the elegance of possibility. And then there was the rotation. The periodic light pulses, observed after the blue outburst, implied a rapid spin, perhaps once every 9 hours. Such speed would generate internal stress enough to tear apart a weaker body. Yet 3I Atlas held firm. That resilience hinted at a tensile strength far greater than rock or ice, more akin to metallic alloys. Again, the planetary core hypothesis made sense. At such densities, the centrifugal forces would be absorbed, not resisted. It wasn't fragile, it was built to last. But what fascinated the scientists most was what this meant for the broader story of planetary evolution. If remnants like 3I Atlas are drifting between stars, then the galaxy is filled with lost fragments of worlds, material archives of cosmic history. Each one carries within it the chemical fingerprints of a different stellar nursery, a different epoch. By studying them, we could trace the genealogy of the Milky Way itself. In that sense, 3I Atlas wasn't just a curiosity. It was a messenger, a relic from a universe younger than our own, carrying the secrets of elemental creation across time. And if we could learn to read it properly, to decode its spectra, we might glimpse not only where it came from, but when. Still, a few things didn't quite align. The level of nickel enrichment remained puzzling. It was far higher than any planetary model predicted. Even the densest cores we know, like Mercury's, don't reach such concentrations. One possibility was that the parent star was unusually massive, producing heavy elements in abundance before collapsing. Another was that the object's long interstellar journey altered its chemistry surface layers, stripped by radiation, leaving only the most stable materials behind. In that case, what we observed might not be the original core composition, but its fossilized residue. There was also the faint but measurable magnetic response detected as it passed through the solar wind. Instruments recorded small deviations, as if 3I Atlas carried a remnant field of its own. That shouldn't have been possible. A magnetic field requires internal motion, molten metals, circulating currents. Could the object still have a partially liquid interior after all this time? If so, it meant that radioactive heating was not merely residual, but active, sustained. A tiny dynamo, still turning after 10 billion years. And that idea, well, it changes everything, because it would mean that this fragment isn't truly dead. It's dormant, yes, but still alive in the physical sense, a planetary heart, still faintly beating, still warm in its depths, still capable of responding to the presence of a star. When it neared the sun, perhaps that warmth awakened, driving the jets, the glow, the energy that puzzled us so deeply. It's strange, isn't it, to imagine something so small, so ancient, reacting after so long a silence. To think that a relic forged before our solar system existed could still respond to sunlight, could still breathe in its own way. It's as though the universe itself remembers, not just through stars and galaxies, but through every fragment of matter that endures. The more we consider this natural explanation, the more wondrous it becomes, because it tells a story of survival, not anomaly. A story in which physics, chemistry, and time conspire to produce something that seems miraculous only because we've forgotten how patient the cosmos can be. Of course, science is never content with poetry alone. The researchers proposed missions conceptual, at least to send small probes to intercept future interstellar visitors, to sample their composition directly, to measure their magnetic fields, to test whether this theory holds. If 3I Atlas truly is the core of a long-lost planet, then others like it must exist. Perhaps hundreds, perhaps thousands. The thought electrified the community. For the first time, we weren't just imagining other worlds we were holding, they're pieces in our sky. And yet, not everyone was convinced. Some pointed to the blue light, the improbable orbit, the timing of its alignment, and said, "Nature is rarely this theatrical." They argued that the natural explanation, though elegant, still required too many coincidences. Others countered that the universe is full of coincidences, and that the human mind simply struggles to accept randomness on a cosmic scale. I suppose that's what makes this story so beautiful. Both sides are right. The event could be entirely natural, yet still profoundly meaningful. It could obey every law of physics and still fill us with awe, because understanding doesn't make wonder smaller, it makes it deeper. And so, by the end of that long year, the scientific consensus had settled tentatively on the planetary core hypothesis, a natural explanation, solid and testable, but still shimmering with mystery. It accounted for almost everything, though not quite. The light, the magnetism, the improbable geometry, all still whispered of something we didn't fully grasp. Perhaps that's the true gift of 3i Atlas. Not answers, but perspective. A reminder that even when we think we've explained the extraordinary, what remains unexplainable continues to pull at us, gently, like gravity itself. And in that quiet pull, the conversation began to shift again. Because if this fragment of a world could survive for 10 billion years, if it could carry a memory of heat and motion across galaxies, then what of the other possibility, the one most scientists hesitate to voice? What if endurance and order this perfect aren't merely the echoes of nature, but of something else, something that once built and then vanished? The question was no longer whispered. It hovered at the edge of every discussion, waiting for someone to ask it aloud.